And our next speaker is Nikos Dimou from the University of North Carolina, Chapel Hill, and is going to be presenting on some strategies in repeated games.
Thank you for the introduction and thank you for having me. Today I'll be talking about a class of strategies that give one of the players control over any adaptive opponent. This is joint work with my advisor, Alex McAvoy, that we did over at UNC. So we'll start things nice and simple, talking about a game that we have already seen too many times the last couple of days, about the prisoner's dilemma. So we have two conspirators and they have two choices. They can either cooperate by staying silent or they can defect by telling on the other person. And this is a game where what is best for them is to cooperate because they will get away eventually. But however, every player has an incentive to defect, and this is what they do. This is the Nash equilibrium. So this type of social dilemma has been studied a lot by scientists, and the basic question that everyone asks is how can we encourage cooperation? And the simplest answer is by repetition. The figures look a bit off. Anyway, so there have been numerous types of social behaviors and dilemmas that have been studied in nature between humans and animals. And what scientists have realized is that, if we allow these individuals to interact sufficiently many times, that they will eventually learn to adapt and cooperate as the game goes on. So this is the subject of the talk. I will be talking about repeated games. I assume most of you are already familiar with the setup, but I will go through it nonetheless. So we have two players, X and Y. Everyone has a strategy set, which is finite, and we endow them with a payoff function. For simplicity, we assume that the strategy sets are finite. However, all the results that I will be stating can be extended to any convex compact strategy set and any type of continuous function. So what's the game? So the players, at every single round, they choose a mixed action. So we allow the players to randomize. But this is not a perfect world. People cannot just read each other's minds. So we assume that the players only observe the pure realized outcomes at every single round. Then the game goes on with probability lambda. This is just a discount factor, and we allow it to take values 0 and 1. And the expected payoff of every player is given by this formula right here. Now, we still need a way to encode, essentially, the behavior of every player. So we introduce these behavioral strategies, which are simple mechanisms that take values into the space of all histories, and they describe how each player should randomize in the very next round. Now, for me to introduce the class of strategies that we will be dealing with, I will take a step back into time and talk about Axelrod's famous tournament. So Axelrod got a bunch of strategies together, and they had them participate in the iterated prisoner's dilemma. Here are some examples. We have always cooperate, always defect, Grim Trigger, which is known for its properties in the theory of equilibria and repeated games, and of course the famous tit for tat. So tit for tat wins in this first tournament, but Axelrod was interested in learning more about the dynamics of strategies in repeated games and in the prisoner's dilemma. So here on the tournament the second time, now with way more participants, and to everyone's surprise, tit for tat wins again. Axelrod gave a number of explanations. He identified 4 basic characteristics, properties that winning strategies should have, and I will not be talking about those today. But a new understanding of why tit for tat performed so well in that tournament came from the fundamental work of Bress and Dyson in 2012. So what Bress and Dyson discovered were the so-called zero-determinant strategies. These are strategies that give one of the players unilateral control over different lines that intersect the payoff region. And more rigorously speaking, a zero-determinant strategy is a strategy that enforces some line to be equal to 0 in expectation. We have some examples here, and importantly, what Bress and Dyson showed is that in the prisoner's dilemma, tit for tat is a fair strategy, which is one of the reasons why it performed so well. So what this means is whenever I play tit for tat, no matter who my opponent is, if the game goes on for infinitely many rounds, then at the end of the day, the expected outcomes will be exactly the same. Zero-determinant strategies have been studied in various other settings, but most works have these main characteristics. So most of the works study linear payoff functions. They have the strategy sets have only two pure actions, cooperation and defection. The strategies studied have the memory one property, and not all of the works, but quite a lot of works assume that we are in the infinite horizon regime, meaning that the discount factor is equal to 1. Now you can see that these characteristics are kind of restrictive. First of all, when it comes to linear payoff relationship, why just study linear relationship? Why just lines? Why not study more complicated payoff relationships like moments of payoffs or the variance? The second is also a bit restrictive in the sense that we have games where you have more than just two pure actions or even with continuous action spaces. The third property is not that unrealistic in the sense that we are infamous for not having great memory. For us, memory one is great, actually. But now we live in the era of AI, and we have AI agents interacting with each other. And these AI agents have the ability to store hundreds and thousands of rounds in the past. And of course, if they can utilize them, then we should allow them to do so. So in that sense, memory one property is a bit restrictive. And I don't think I have to talk about the last one. I don't know about you. I've never played a game for infinitely many rounds. So these characteristics lead to three main problems, which I will be talking about today. The first one has to do with payoff control, and it's very generic and a very natural thing to ask. How much control does a player have against their opponent? And now I'm not just talking about the prisoner's dilemma. I'm talking about any game, any multi-action game, so we assume more than two actions, in any sort of discounted setting, so the discount factor can take any value from 0 to 1. And of course, we're not just interested in linear relationships, but in any kind of payoff relationship. The second main problem has to do with memory. So how much memory is needed? Is memory one sufficient? One would assume that the more memory you are able to store and utilize, perhaps the more payoff relationships you are able to enforce. And the third problem has to do with computational tractability. This is related to what Nicoletta talked about previously, that we have this dimensionality issue when we move from two pure actions to n pure actions, and we move from memory one strategies to memory n strategies. These are much harder to study, and it has been shown that the dimension blows exponentially when one tries to identify zero determinant strategies using the techniques of presentation. So we will be answering these three questions. But in order to do so, we have to extend the notion of zero determinant strategies of presentation. So we say that the strategy is autocratic, given some payoff function phi that we're interested in. And again, this function phi can be anything we want. So we say that the strategy is autocratic simply if it sets this expected value of this function to be equal to 0, no matter how the opponent behaves. And of course, you can see that if phi is taken to be any line that intersects the payoff space, then we get back the zero determinant strategies of presentation. So what presentation did, and many other works that followed, is they try to identify sufficient conditions for the existence of such zero determinant strategies, not just in the prisoner's dilemma, but in other games and other settings as well. So what we would like to do here is try to identify sufficient conditions for the existence of these much more generic autocratic strategies. What we managed to do is go one step further and manage to identify both sufficient and necessary conditions. So let's say that you're interested in seeing if you can control any adaptive opponent. So you have some payoff function phi here, you have some discount factor lambda. We have that there exists some strategy that enforces this relationship to be equal to 0 in expectation, if and only if there exists some set of mixed actions, some initial mixed action sigma x0, and some sigma x star strategy. This will be the autocratic strategy, along with a potential function psi, so that this so-called next round correction condition holds. Now, this represents an extension of what Alex showed 10 years ago. They showed that this condition, in its deterministic form, implied the existence of autocratic strategies. We showed that the average type extension of this formula is also a necessary condition. And you can think of this function psi as a mechanism that essentially describes how one this function essentially psi essentially corrects previous error or mistakes, so that at the end of the day, the function phi will be equal to 0 in expectation. Now, even though this is a very nice characterization to have, you can imagine that it's not entirely obvious how one finds as a function psi or a strategy. But fear not, because we have a much more practical characterization. So we have two sets here, these phi plus and phi minus sets. And you can imagine that a mixed action, this phi plus set is a mixed action that allows the player to take advantage and exploit, let's say, their opponent with respect to the function phi and the zero level set. And this phi minus set, you can imagine it as a set of mixed actions that essentially translate to player X being willing to give more and lose with respect to phi, again, with respect to the level zero. So what we showed is that there exists some autocratic strategy with respect to the function phi that we're interested in, if and only if these two sets are non-empty and the game is sufficiently long. So we identify a lower bound on the discount factor lambda here. And the nice thing here is that this is pretty easy to compute simply because it only depends on the function phi that we're interested in enforcing. So these two characterizations give an answer to our first problem about how much payoff control does a player have against any adaptive opponent. Now moving to the second question, the memory question, we introduced these reactive learning strategies. Alex actually introduced them a while ago. And you can think of a reactive learning strategy as a strategy that takes into account the player's own previous mixed action. So now the player does not remember what the pure outcome of their mixed action was. They actually keep track of their own randomization mechanism. But they still cannot read their opponent's mind. So they still keep track of the opponent's pure realized outcome. And this is, you can think of this as a slightly more sophisticated memory one type of strategy, but it still has the memory one property. You only need to remember what happened in the previous round. And the surprising second result that we showed is that memory one is all you need. So if you're interested in a payoff relationship phi, and you want to see if you can set it to be equal to zero in expectation against any opponent, then if you know that there exists some autocratic strategy, you can always replace that by one that is reactive learning. And more importantly, the strongest part here is that your strategy is a two-point strategy. And this two-point property means that there exists two mixed actions, tau plus and tau minus, that are fixed a priori. And you only need to randomize between these two actions using a probabilistic mechanism, this P star function here. And in our work, we have a way to compute this tau plus and tau minus, and we also have a closed form solution for the P star function. So what this result says is that if you can actually take control against any adaptive opponent and enforce any kind of payoff relationship that intersects your payoff region, then you do not need any kind of memory. Memory one is sufficient. And no matter how many pure actions you have, at the end of the day, you just need to randomize between two mixed actions. Now we move to the third problem, the computational tractability. To this end, we say that the function that we're interested in is enforceable if it can be enforced to be equal to zero in expectation. So if there exists some autocratic strategy. And you can think of that, we're interested in a payoff relationship. We see, can we actually take control of an opponent using this relationship? And we would like to see how fast we can actually identify whether or not we can do this. The problem of identifying whether you can set some function phi that you're interested in to be equal to zero in expectation, this problem can be solved in polynomial time. Importantly, what we showed is that if you can identify that the function phi is enforceable, then the minimum length of the game, along with a two-point reactive learning strategy to enforce it to be equal to zero in expectation, both of these quantities can also be computed in polynomial time. So this solves the dimensionality issue that people have had previously by using the standard techniques of presentization. And the method is you have to solve two linear programming problems. I tried to include them here. They were too large and complicated, but they are in the paper. Okay, if you were bored, now it's a cool figure for you. What we see on the left is the standard prisoner's dilemma with values 3, 0, 5, and 1. And on the right, we have a heat graph. And I will explain what this is because it looks like a handful. So we studied all kinds of lines that the player can enforce in the iterated prisoner's dilemma. What you see on the right is a heat graph that shows exactly which lines are enforceable and what is the minimum discount factor to do so. So we write the lines that we're interested in this form. These have a nice game theoretic interpretation when it comes to extortionate and generous strategies, which is why we write it like this. But we use polar coordinates instead for the heat graph. So the radius r, which corresponds to this section here, is given by this formula right here at the bottom. and the angle theta, which is essentially the angle of the line that we're interested in enforcing to be equal to 0 in expectation with a reference line y equals x, then this is given by the formula in the bottom right. Okay, let me start simple. So let's take the case where the angle theta is equal to 0. This means that we're interested in seeing if we can enforce the line y equals x. What the heat graph says is that for any value of r between 0 and 1, this corresponds for any value of kappa between p and r, then we can do so. We can enforce it to be equal to 0, but the minimum discount factor is equal to 1. And this is not something new. This is not surprising, right? We have seen previously Preston Dyson in their work that tit for tat is a fair strategy. Now, as we open up the angle of theta and we move the line to the left with respect to the reference line y equals x, let's say up to the value pi over 4, then this line is essentially orthogonal to the pi y-axis, which means that we're interested in equalizers, taking entire control of the opponent's expected outcome. And we can see that for all these lines, as we move them left and right, we can always enforce them to be equal to 0 in expectation. And the minimum discount factor to do so is right over around here. It's 1 over 2. So one can keep going, and you can still keep rotating this line and this opening up the angle theta, which will correspond to negative values of the factor chi. And up to this point, up to the point where we have this yellowish dust line over here, you can see that all such lines are enforceable. But after this point, something interesting happens, actually more than one interesting things. Firstly, we see that we have this gray region on the left, and this corresponds to all lines that cannot be enforced to be equivalent to 0 in expectation. What we also observed is that there exists a family of lines that can be trivially set to be equal to 0 in expectation, so you just have to play one round. And this corresponds to the yellowish curve that you see inside that region. Another thing is that we see this monotonicity property of the discount factor lambda. And inside this dust region, it is actually pretty small. But importantly, what this dust region here means is that the 2 points that you have to randomize between, if you remember, I previously mentioned that you just have to randomize between 2 mixed actions. Inside this yellowish dust region, these mixed actions are strictly mixed. Everything outside, so in the wedge over here and on the colored area here on the right, you just have to randomize between cooperation and defection. If you want to enforce these lines in this region here to be equal to 0 in expectation, and you want to do so with a minimum discount factor, the minimum length of the game, you actually have to randomize between strictly mixed points. And as we move to the left and we explore more negative values of chi, then we get this wedge over there. And for theta equals pi over 2, you just take the line that it is orthogonal to the reference line. It connects the 2 extreme points, and you can only do that in the infinite horizon regime. Now I have some time to briefly show you some other games that we studied. First, the nonlinear donation game. This is the donation game with 2 different types of benefit and cost that you have to take, B1 and B2. And this is the heat graph that we found. We also studied the asymmetric donation game, simply because the symmetric one was simple and a bit boring. And this was also nice because it highlights here the difference between what a fair and what an equality strategy is. And we get this nice heat graph on the right. We see that when the angle is equal to pi over 2, then you can enforce all such lines trivially by playing only one round. And we also studied the Hogdog game, which has this cool-looking fin of a shark heat graph. And yeah, I will stop here. Our paper is on archive if anyone wants to check it out and give us sort of some feedback. Thank you.
Question?
Thanks. Great talk. Great work. Well, just some clarification. So I understand that your main result is that whether or not certain phi is like enforceable or like it is enforceable, you can do it in polynomial time. And you have these formulas of how to like with the min and the max. I was wondering how you like if you could say a little bit about how you derive that and how the memory reduction works. I think I was lost at that point. Like in those two slides, if you could give an idea of how you arrived at that, and if the memory reduction slide was
Here?
yeah, actually the next slide. I was just curious how you
Yeah. So the first one, the problem of identifying whether a relationship that you're interested in is equal to 0. And the reason why you can do this in polynomial time, well, we saw from the first result that it suffices that these two sets are non-empty. This is just a linear feasibility problem. Simply because you're in the setting where the strategy sets are finite, then you can write this as, you can write all these values as a matrix form in a capital phi, let's say, sense, and you just solve two linear feasibility problems. The second part is slightly more ambiguous in the sense that you're not computing in polynomial time the actual strategy. What you are computing in polynomial time as these two mixed actions that you have to randomize between. And what you compute is a base here. You compute all these points, which are finite. So you compute this base, and this is actually the base, the only thing you need, because this P-star function is linear with respect to the mixed actions that the player takes into consideration when they want to go into the next round, let's say. So you do not actually compute the strategy itself, you compute the 2 points and the P-star function that you need to randomize. And then you're done. This is all you need because this is a closed form solution.